welcome back. Today's Tuesday, so hopefully everyone had a good weekend. All of that. Weather is relatively nice, even though I think it's going to get warm again for the next few days here. So there we are. I don't know. Anyone do anything fun and exciting over the weekend? No? What did I do? Oh, I went to a soccer match. Cincinnati Club soccer match Saturday night, but other than that, I didn't really do anything at all. So, first and foremost, I know that, the exam is on your mind, I'm sure. I'm going to hand the exams back at the end of class. I'll always do this for a couple different reasons. The first, easiest reason is after you get the exam back, you can just leave. So that'll be the end. And it'll thin people out and make it easier to hand back the stuff. But, obviously, bear with us. Yours will be the last one, I'm sure. Whoever you are, it'll be the last one in the pile. So you have to wait till the very end. The other reason why I do it is because what I'm hoping you'll do is take the exam and then look at the answer keys. The answer keys are posted for you on Blackboard. And by doing that, find out what you missed, okay, and then see why you missed what you missed. That way you can kind of review and brush up on some information that maybe tripped you up a little bit. Because when it comes time for the final is going to be over material that are on the other exams. So the 4 exams together build up the final. So if you missed it here, I don't want to see you missing it again later for a simple reason or something like that. So there's a good reason to do that. So what I always tell students to do is to take the exam and do 2 things. Number 1, make sure the points add up correctly, because by all means I may add up the points incorrectly or something like that, so you get the credit that you should get. And then 2, understand why you missed what you missed, so that you don't miss it again later on in the course. As an added argument for doing that, we're going to be building upon the ideas of the Chapter 1 exam stuff all the way through the course. So if you don't understand it now, next week you're going to have a problem. 2 weeks from now you're going to have a problem. 2 months from now you're going to have a problem. So don't fall behind at this point and then get in a hole and can't get yourself out. That's really how students get in trouble in this course, is they think at the beginning, oh, this is all good and easy and I got plenty of time to catch back up and stuff like that. Well, before you know it, you've got too much stuff and you're not having the time to get caught up and so on. So don't let that happen to you. Questions about that at all? Okay. Scoring-wise on the exam, we'll run through the scoring and you'll be able to see what you got out of the 200 points and so forth. It's on your paper. But as a class as a whole, the average was, I think, a 73 or 74%, which not good. Which is exactly where it should be, considering that is the C range as it is. Now, in general, we have other opportunities to bring the score up if you're not happy with that. We have the clippings that are usually relatively highly scored, the homeworks you can do in limited amounts, things like that, which will bring the score up if you don't, but at the same time, don't just ignore your exam scores. I mean, don't think that if you got a 20%, by doing the homeworks, you're going to get it back up to a 70% or something like that. Okay? Mathematically, that's not the way it works. Now, that average was before the extra credit and so forth, so that will bring it up some as we go through it, but that's where we stand. I'm actually happy with a 73, 74. Traditionally, the first exam is a little bit higher, usually right around there, so right where it normally is. And then later on it goes down a little bit more because there's more new information and so forth. But overall I was relatively happy with it. Okay, questions about that? Yeah?
So you're going to be giving us our test back today?
I am.
Okay.
At the end of the day. And you will be able to keep that forever and ever and ever. I mean, I won't recollect them or anything like that. Okay, anything else? Yeah.
Some of the answer keys where you wrote in the information, like on the math portions, you can't read that. You can't see it on black.
Oh, it didn't copy over very well? Okay, well, I'll rescan it and see if I can get it a little darker.
Okay.
So, okay, yeah, I didn't notice that when I just scanned through it real quick. But yeah, I can absolutely do that. No problem. Yeah, also, if you can't read my handwriting or something doesn't make sense, just let me know and we'll square it away too. Okay, so I guess with that, we're going to get back into material. I really don't have too much more for announcements and so on, so we'll just get started. Last time, when we were in lecture, and I guess that was a week ago at this point, we were talking about the 3 different experiments that showed the makeup of an atom. Now remember, atoms themselves are incredibly, incredibly small things. They can't be seen with the naked eye. And then we're doing things and doing experiments related to them to find out what makes them up. So we're really talking about the makeup of atoms as we go through. And I thought we would just start off with just a quick refresher about what the 3 different experiments that we talked about. Now there are a lot more experiments that were done. These just kind of led to the basics of the atomic structure, particularly related to electrons. So the cathode ray. In the cathode ray, we were able to find the mass to charge ratio for electrons. So here we found basically the relationship between mass and charge. We weren't able to separate them because of the way the experiment was done, but from the information we got, our first hint that there is something smaller than an atom that's characteristic or present in all different types of atoms, and then that's the electron, and along with that, the mass and charge ratio of it. After that, we looked at the gold foil experiment, or sorry, the oil drop experiment, and this separated mass and charge. So we can find for an electron what the mass of an electron is and what the charge of an electron is. Now, chemists, we say the mass of an electron is 0, as you'll notice up there on the board. It does have a mass. Don't think of it as no mass at all, but the mass is incredibly small, and because it's incredibly small, we just round it off to 0. So through the oil drop experiment, we were able to separate the mass and charge for electrons. Similar experiments were done with the other particles as well, leading to our various understanding, which we've got up there on the board. So from these 2, we've got the mass and charge of the electron, and through analogous ones, we've got the proton and, well, the neutron as well, we may as well say. And the last experiment we looked at was the gold foil experiment. And the gold foil experiment discovered the nucleus. And the nucleus is the mass of an atom. So if we have our picture of the atom here, what we're talking about in the nucleus, traditionally we draw it at the center of an atom, but that little spot has all of the mass of the atom inside of it. And we know this because in the experiment, when the particles were shot at it, most of the particles passed right by, which meant that they never hit anything of any significant mass associated with it. So they would just pass right through. The example I used earlier when I was lecturing about this was like chicken wire. If you think of like a chicken wire fence where you've got just a little bit of chicken wire and you shoot a BB at it, the BB would most likely go right through the chicken wire, because it wouldn't hit any solid things. But then every once in a while, you would hit a little piece of solid and it bounce off in some direction. Okay, the same thing here. When you're looking at atoms and you're shooting at particles at them, almost all of the atom is empty space, except for this little spot of mass in the center. And because all of the mass of the atom is in the center, and we call that the nucleus, we know that that's going to be the protons and neutrons. Because protons and neutrons have mass, so they must be located in the nucleus there. Now, the size of the nucleus is not to scale in this at all. I can't make a spot small enough for it. The analogy I remember about this is if you have an atom and you make it roughly one atom the size of the Great America Ballpark downtown, if you go to the center of it and you put a period from an end of a sentence in your book out there, that would roughly be the size of the nucleus. So the entire atom would be the entire ballpark, and then one period from your book would be the size of the nucleus there. So when we think about it, you know, almost all of it is empty space. Okay? 99.99999, however many nines you want to say, is going to be empty space. And this little tiny bit that's left over is where your mass is located at. So our drawing here, we have electrons that are on the outside of the nucleus with no real mass associated with them, and then we've got the little bit in the center there that has the mass associated. So this is called Thomson's, wait, no, I'm getting confused. Yeah, it's not Thomson. I knew it as soon as I said it. Rutherford. Rutherford's atomic model. Thomson did the gold foil experiment. And this model is the first one that put forth the idea of a nucleus. Okay, do you remember that from last time? Kind of a refresher for the most part. So once we understand where the various components are, and we know what these various components are, the protons, the neutrons, and the electrons, we can take a look at what makes atoms actually atoms. So Dalton's atomic theory says that atoms of an element are the same, atoms of different elements are different from one another. Well, all atoms contain protons, almost all atoms contain electrons, or actually they all contain electrons, and almost all contain neutrons. So those are present in all different types of atoms. So what makes one atom of an element different from another one? And what it really is, it's the combination of those components. So each element's atoms have a different combination of protons, neutrons, and electrons that define it. And because of this, they act differently from one another. So to understand this, we have to talk about something called isotopes. And this is going to allow us to start talking about what actually makes up any given atom. So an isotope is two atoms of the same element, but they have different masses from one another. This is actually an exception to Dalton's atomic rule that says that two atoms of the same element are the same. Well, there are cases where two atoms of the same element have different masses, and they're called isotopes of one another. They're actually fairly common throughout the periodic table. Now they have different masses. So for example, hydrogen. Hydrogen has three different isotopes that are up there on the board. There is hydrogen 1, hydrogen 2, hydrogen 3. When I say hydrogen 1, that means that it has a mass of 1. Hydrogen 2 has a mass of 2. Hydrogen 3 has a mass of 3. They do have names that go with them. Protium, but protium you may see in science fiction shows. Normally in real life we just call it hydrogen. So the normal isotope you just use the normal name for. Hydrogen 2 is called deuterium, and then hydrogen 3 is called tritium. If you guys have ever watched the Spider-Man movies, I don't remember which one it is. I think it's Spider-Man 3, the one with the octopus guy in it. I'm not a Spider-Man person. they talk about tritium being like the rarest material on Earth, and he's got this little tiny sample of it. Well, there's a lot of scientific flaws with that. Tritium itself is actually not that rare. If I had a glass of water up here, I would have some tritium in it. Okay? It's just out there and so forth. And then second, it's not a solid, it's a gas. So you can't have a little solid ingot of it. It's a gas because it's hydrogen. And hydrogen's a gas. So there's tritium. Now, the masses that I said 1, 2, and 3 are what tells them apart. And that's also how you know what they're made up of. So hydrogen 1 can be written this way, or it can be written like this, with a 1 and then the H. And then for completeness, there should be a 1 there as well. So these two things are equal to one another. However, normally when we draw out this way, we leave the 1 off of it, like it is up there on the overhead. That's because when you look to the periodic table, whatever number that is, that's the number that's with the element. So hydrogen 1 would look like this. Carbon 14 would look like this. So this number on the bottom is whatever the number is on the periodic table. So carbon is 6, hydrogen is 1. That is called the atomic number. And every isotope of a given element has the same atomic number. So for hydrogen here, there should be a 1 here, a 1 here, and a 1 there. Because they all have the same atomic number of 1. And that's actually what defines what element an isotope belongs to. So anytime you've got 6 as your atomic number, that atom's always going to be carbon. Another thing about the atomic number is always equal to the number of protons. So whatever your atomic number is, that is the number of protons. The number of protons defines the element. So anytime you have 6 protons, that's always carbon. If you have 1 proton, like up here on the overhead, you see you have 1 proton in the center of all of them, that means they're all hydrogen. If I have, 27 protons, what element would that be? Cobalt. CO. CO is cobalt. Okay? And that's really all there is to it. If I have 82 protons, then I look, 82 is lead, Pb. Pb is lead. And that's all that there is. That's all you need to do and know the number of protons. So if I want to say, how many protons does oxygen have? We go to the table, we look at oxygen. Oxygen is atomic number 8, so that means that we have 8 protons. How many protons would we have for calcium, Ca? 20. 20, Ca. Okay, Ca is in the second column of the periodic table. They're about halfway through it. And that's called your atomic number. The hardest part of this is the fact that on the isotope symbol, the atomic number is at the bottom, where on the periodic table, it's on the top. So that gets a little tricky there. But you just remember the atomic number is the smaller number. So out of the numbers that we're talking about, the atomic number is always the smaller one. So that's the number on the bottom. And you can see how that corresponds to the element symbol here. The number at the top is the atomic mass. Atomic mass. Now this is going to depend greatly on what isotope it is. So if we look at the 3 hydrogens on the board, you see they've got 3 different ones. But the atomic mass is always equal to the number of protons plus the number of neutrons. because protons have a mass of 1, neutrons have a mass of 1. So if you add up the number of protons plus the number of neutrons, that is going to be equal to your atomic mass. So on the overhead, hydrogen 1 has a mass of 1. And it has a mass of 1 because we only have 1 proton there. Hydrogen 2 has a mass of 2 because we have our 1 proton plus 1 neutron. So if this is a mass of 1, that's a mass of 1, add them together, we end up with a mass of 2 overall. Hydrogen 3 is again 1 proton because it's still a hydrogen, and then 2 neutrons to give us a mass of 3. Let's try, well, does that make sense? I want to do a couple examples here just to make sure we're all on the same page because this is really important going forward. Okay, so let me make up something. Let's do oxygen 18. So for oxygen 18 on your paper, write down how many protons it would have and how many neutrons it would have. Okay. Everyone got their ideas? Okay. So for oxygen 18, it's oxygen and the atomic number is 8. So the number of protons is equal to 8. Then the number of neutrons is going to be the mass minus the number of protons. So that's going to be 10. Questions there? Yeah.
Okay, you said that the atomic number is always the number of proton and neutrons?
It's always the number of protons.
Protons.
Protons alone.
Okay.
The mass is actually the number of protons plus neutrons.
And that's the top number.
That's the top number in the isotope symbol. Yep.
Okay.
So you just subtract
So-
the mass with the atomic number.
Flip it, but yeah, you subtract the atomic number from the mass.
But
Yeah.
you said you subtract the, what did you say about the
Okay,
subtraction?
so to find the number of neutrons, it's going to be the mass minus the number of protons is going to be your number of neutrons. Because if number of neutrons plus number of protons is equal to mass, and you'd bring it over, and it would be a subtraction there. Or you can just think of it logically. If every one of these 8 is equal to 1, that gives you a mass of 8. How much more mass do you have? You have 10 more mass to make up. So 10 more would give you 10 for your neutrons. Okay, let's try one more. Let's do something a little more complicated. Let's do, why am I even trying to figure something out? 110. So let's do silver 110. Everyone got their ideas? Okay, so the first thing we have to figure out is how many protons does silver have? So how many protons does it have?
47.
47, perfect. 47. And then your number of neutrons is going to be 110 minus 47. And assuming I did my math right, I end up with 63. 63 there. Everyone getting an understanding here? So these are when we're talking about specific isotopes, like oxygen 18 with a mass of 18, silver with a mass of 110, and so on. Couple things for this class to keep track of. If an isotope is not directly given to you, if I was to just say how many protons and neutrons were there in silver, then you would go to the periodic table and you would find the closest mass to it. So silver is right here on the periodic table. It's 107.8. So as far as this class is concerned, we can just round to 108 as the normal silver. What would the normal iron be? Well, it's 55.8. We would just round to 56. If you want to do 55, that's fine. I'll be okay with that. But either one of the two. Right? So if a mass is not specifically given to you, then look to the periodic table and find out what the mass is. But if it is given to you directly, then use whatever is given to you. Does that make sense? No? Okay. I think that's it for that right now. Yeah? Okay. So here is the isotope notation again for us in our notes. The atomic number, this is the number of protons which defines what element something is. And that's given there, and then the mass is on the top. And this allows you to do calculations to find the number of protons and the number of neutrons relatively easily, I think.
And this is called A to Z notation.
That's one of the names of it, yeah. A to Z or isotope notation.
So would you refer to A to Z or isotope? Just so like on the test we would know which one to go by, you know?
I'd probably call it isotope.
Isotope, okay.
A to Z is probably better, but I'd probably call it isotope.
That's fine, I just need to know which
No,
one.
no, yeah, if, you know, on the, yeah, you would know it, but I know what we're gonna do for the next week or so, couple weeks, so by that point you'll get tired of it.
Okay.
Yeah. Okay, so this allows us to find the number of protons and the number of neutrons. The third particle of our atom is electrons. So let's right away go ahead and figure out how to know how many electrons we have. Well, the way that you're going to do that is you're going to look right here to see if there's any symbols in that position. If there's no symbols, so if, and they're called charges, if no charges, then the number of electrons is equal to the number of protons. So in this case, there's nothing there, so the number of electrons is going to be equal to 47. If, on the other hand, we have this, then we would still have 47 protons. We'd have protons 47. The number of neutrons would be 63. But if it had, let's say, a negative there, or a -1, that means that it has one more negative charge than positive. So looking at the three types of particles inside the atom, we have the protons, neutrons, and electrons. Protons are +1. Neutrons are 0, so we don't have to worry about those now. Electrons are -1. So if we have one more negative than we have positive, how many electrons would we have? One more negative than positive. 48. 48. Because what that means is we have 47 positives and 48 negatives. So since we have one extra negative, that's going to give us a negative there. And that would be a -1. If you had 2 extra electrons, then that would be a -2. If you have 3 extra electrons, it would be a -3, and so forth and so on. All right. What if we go the other direction then? If we have 110, Ag 47, and we're going to do a +2 this time. So the number of protons is still 47. The number of neutrons is still 63. And the number of electrons. Now, when you have charges, you're either adding or subtracting electrons. You can't change anything else, only adding and subtracting electrons. So what the +2 means, it means you have 2 more protons. Okay, so you have 2 more protons and electrons. That's what a +2 means. So if I have 47 and I have 2 extra protons, how many electrons would I have?
45, because it's going to subtract.
It's going to be 45 because I have 2 more positives than I have negatives. Okay. So what happens in this case is we actually take 2 electrons away, and then that gives us our 2 extra positives. This is actually really tricky because you're adding and subtracting negatives when you're doing it. It's like subtracting a negative is the same as being a positive. So it's a little bit tricky in terms of keeping track of it. So what I always do is I double check in the end. I have 45 negatives, 47 positives. So I end up with 2 extra positives, which is what the +2 is here. Yeah?
So basically, you're saying if you have a negative charge, then you add it
You add electrons? Yep.
to, how I'm seeing it is you add the negative to the number of protons, and that comes up with your electron, your E's.
Yep.
And then if it's positive, you just subtract.
That is, you can absolutely do it that way. Yeah. Okay, so let's try another one. Let's do Cl minus, chlorine 37 minus, and see if you can figure out the number of protons, the number of electrons, and the number of neutrons. Let's say 30 seconds or so. Everyone have their ideas? Okay. So the number of protons, well, it's chlorine, so we're going to look to the periodic table and see that the atomic number for chlorine is 17. So we're going to have 17 protons. Neutrons. Yep, that's right. So the number of protons is 17. The mass is 37. So 37 minus 17 is going to be 20. And then our number of electrons, 18. Everyone agree with 18? Okay, that's correct. It's 18. You have a minus here, so that means one extra electron. So 17, and then our one extra is going to give us 18 there. Does everyone feel comfortable with that right now? Yeah, we're going to get a significant amount of practice with it as we go on to the next topic. So if we have, yeah.
So did somebody say, when you see the negative, obviously you would just do the exact opposite, and then if you would see the positive, you would do the exact opposite of that? When it comes to the, for
Yeah,
electron.
that's basically what she was saying,
Is that
yeah.
okay?
So here, if it's a -1, then you would add 1. If it's a +2, then you would subtract 2. So you can keep track of it that way. And I don't see a downside to it as long as you can keep track of that in your mind. That's actually just throws me for a loop saying it, but that's just me. I don't think that way. So the way I think of it is electrons are negative. So if I add an electron, it's going to subtract 1 from the overall charge. And if I take 1 away, it's going to add 1 to the charge. So, but again, either way, it's going to be perfectly fine. Okay, so now this explains some things about atoms. So for example, chlorine has this makeup of components to make this atom of chlorine. Silver has this component makeup to make silver, and so on. So we're really starting to get to the point now to where we can start seeing why things behave the way they do. Chlorine, for example, when chlorine goes into reactions, it's always going to make a -1. We won't worry about why that is right now, but know that it always makes a -1 when it forms compounds with metals. And the reason it does that is because of the makeup here. So by understanding the makeup, we can start to see why it is. Now, I don't expect you guys to see why it is yet, but we will get to that in the next few days, actually. Or next couple weeks. All in all. And that's why it's so important to be able to figure out the makeup. Okay, last chance for questions here. So we talked about where these components are in the atom. So if, for example, I were to draw out the chlorine atom here, you would have your nucleus. And inside that nucleus, you would have 17 protons and 20 neutrons. And they'd all be packed together inside this center location here. But we haven't talked about electrons. We said that they're spread out through the rest of it. So you've got 18 electrons in this case spread all throughout the rest. But that's not really useful in understanding why they do what they do. So the next section that we're going to talk about is actually how we think about electrons inside of it. There are two major theories that we're going to talk about. The first one is the Bohr model. The Bohr model is based on the planets in the universe. So this is the one that most people are exposed to first in wherever they're learning, if they've ever learned about electrons, atoms, and so forth. And in this case, you have your nucleus in the center, and then you have orbits around the outside. And then electrons sit in these orbits, and then they spin around the center. Just like a planet going around the sun. And this is the Bohr model. And then after we talk about the Bohr model, we're going to talk about the quantum model, which is an advancement, an improvement upon the Bohr model. It's useful in understanding, well, it understands everything, but you use it when you're trying to expand slightly more complex things because of the subtleties of it. Just like the planetary model, for example. Remember, when I was a kid, I made a model of the planets, and it had Pluto. And Pluto circled around as a normal circular orbit and so forth in my model. Pluto itself doesn't circle in a normal orbit. It's actually an oval. So you can think of it as the quantum model refines the Bohr model to better explain things. But in doing so, it does get slightly more complex. So we're only going to look at the most basic level of the quantum model as we're going through things. Have you guys seen the Bohr model before? Pictures like this? It's on TV and so forth. Whenever they're drawing something chemistry-wise, they always draw circles. I don't know. It seems easy to do. So the story of the Bohr model, actually, is that Niels Bohr, he was a physicist and a mathematician. And he decided that he wanted to tackle the problem of understanding where light comes from for given elements. So when you heat up a given element, only certain colors of light actually come out of it. So this is characteristic for every element. So here's the hydrogen spectra and the visible lines. You see 1, 2, 3, 4, 5 colors, lines. And they're actually very, very narrow coming out of hydrogen. If you were to do helium, you would see different spectrum. If you were to do neon, you would see different spectrum as well. And this is why different gases give off different colors. Neon is red, mercury is blue, hydrogen is blue, I think. Sodium, no, maybe sodium or chlorine, I forget, is green. There are different colors associated with each different element. And it's actually one of the oldest tests that chemists had, because if you imagine it, it's actually really easy. You have a flame, you throw some chemical in it, and you watch what color comes off. And that color is characteristic for whatever element it is. So you can do this and actually see what elements make something up. Another interesting example of this is helium. Helium is number 2 on the periodic table. Helium was actually discovered in the sun before it was discovered on Earth. And the way that this was they were looking at the light that comes out of the sun, and from that they noticed that there were certain bands that didn't match up with anything else. And from that they were able to identify helium as an element, and then it was confirmed on the Earth when it was actually discovered. So each atom gives out specific colors when you energize them. So he wanted to explain this. Chemists had no idea really why this occurred, but he set out from a mathematical approach to explain this. He used the solar system as his basis, and that's why he's got orbits, and then the nucleus in the center and so forth, and he did a lot of math. A lot of math. Math I don't understand. So we are just going to say he did a lot of math, and he ended up explaining things perfectly. As a matter of fact, from his model of hydrogen, he can calculate, and I actually did this once in school because they made me. I calculated where these lines would be exactly, and they're dead on to where they should be. So he actually did it without the experimental stuff. He did the math, found the values, and then said, oh, these match perfectly for what we're looking for. So it's a real example of math being able to show why they do what they do. So here's the real explanation for you guys. When you have an atom, we have electrons that are sitting inside these rings. Now if I add energy to it, that energy could be electricity, it could be fire, it could be chemical energy, it really doesn't matter. It has to absorb the energy. So the way that it absorbs the energy is the electron moves out to an outer ring. And when the electron moves, that's called the excited state. After the electron moves, and this is when an atom has absorbed energy from something. So it's sucked in some energy and is just holding it there for a moment. Then once that moment is up, the electron is going to move back down to one of the other orbits further in and give that energy back off. So that's energy is released. And as that energy is released, that energy is always released as light. And when you look at it, every amount of energy corresponds to a certain color. So as it goes from here back down to the first one, it's going to give off a color. So let's say in this case it's purple. So the transition from here back down to there is going to give off one of the purple bands. Then it could also go from here down to that orbit. And when it does that, it gives off a different color. So this one, let's say, is the light blue one there. So for each of these steps that it goes down, it's going to give off a different color associated with it. And that's why we see multiple bands that occur. So the light that we see when we energize something is actually energy being released back out of the atom, and that released energy out gives us the various colors that we see. So let's talk about it in terms of a practical example of the lights in this room. Okay, the lights in this room. The way the lights in this room actually work in terms of chemistry and so forth is you hit the light switch. That's going to pass electricity through the gas inside the light bulbs. When that electricity goes into the gas, it's going to soak up some of the energy, and the electrons are going to move outwards. Then, in a matter of milliseconds, that energy is released when the electron goes back down. That gives off the light. So it sucks up energy from somewhere, and then when it releases that energy out, it gives it off as light. These light bulbs have mercury in them, so if they were just plain bulbs, they would glow with a bluish color to them. There's a special coating on them that actually makes them glow different colors. So mercury is going to glow blue. A neon light. You guys ever see neon lights? Okay. Real neon lights are red when they don't have coatings on them. And that's the same way. When you pass electricity through the neon and then it gives up the energy, that energy that it gives up corresponds to the red color. So this idea of the electrons moving, matching up with the spectra proves Bohr model is a good one. And that's the way we think about it. Questions about the theory behind Bohr's there? I'm not sure what. Okay. So how do we actually use it? We are going to use it to think about where we set electrons and how we place electrons inside of the atom. So our chlorine example has 18 electrons. So chlorine minus was 18 electrons. So how do we place these electrons inside the atom? Well, all you've got to do is you start in the center and work your way out. So the first ring, every ring can hold up to 2 n squared electrons. So if you have ring 1, 1 squared is 1 times 2 is going to be 2 electrons that the first ring can hold. We have 18 to place, so we're going to put 1, 2 in that first ring. Well, we haven't placed them all yet, so let's make another ring. You can just keep adding rings as long as you want. So we add another ring. How many will this one hold? Well, 2 squared is 4 times 2 is 8. So that's going to hold 8 of them. So we'll place 8 more. 1, 2, 3, 4, 5, 6, 7, 8. So 2 plus 8 is equal to 10. So we have 8 more to go. So the third ring, 3 squared is 9 times 2 can hold up to 18. So here we've got 1, 2, 3, 4, 5, 6, 7, 8 as we go around it. So now we've placed all of our electrons. So this is the Bohr model for chlorine minus.
So will that go for any element?
Yep. The same process goes for every element.
Okay.
Okay? And we'll do a couple more examples here so we're all on the same page. So all you do, or what you do is you start in the center and just work your way out, filling the orbits. Once they're filled, you just move out to the next one. So I fill the first one with 2. Okay, great. Move out. 8 on the next one. And then we have 8 more to go on the last one. If I had 4 more to go on the last one, then I'd put 4 in the last one. If I had 20 more to go, then I would have to add another ring as we go through it. Okay?
So you stop where the, what is the, I'm sorry, is there a name for the large number, like 18? What is the name for that? Is that
It's just the number of electrons.
Okay, so you would stop when you reach the number of electrons?
Mm-hmm.
Okay.
Yep, when you place all the electrons, then you stop. Yep.
Explain again the 2 and 2 on the.
Okay, so from his mathematical derivations, he found that each orbit can hold 2 n squared electrons.
So that's just universal.
And that is universal, always true.
Got it.
And I mean, if you're a math major, you can probably figure out the math associated with it, but yeah, I don't. But I just know that in the end, this formula keeps spitting out. Okay? And it works unbelievably well. Yeah.
Can you like show how you plug those numbers in?
Of course. So, like here to get this? Okay. So, you start with the orbit number, which is basically how many rings. So this is the first ring. This is the second. This is the third. To find out how many electrons it holds, it's going to be 2 n squared. So for the first one, it's going to be 2 times 1 squared. Okay, 1 times 1 is 1. Multiplied by 2 is 2. So the first one holds 2. The second one is 2 squared. 2 squared is 4. Multiplied by 2 is 8. Okay. And then it's just a matter of funneling it through the
Had a
same.
slow moment.
No, not a problem at all. I'd much rather you ask and be sure you understand than not understand. This seems incredibly, incredibly simple, but it really is like the key to understanding chemistry.
So will it always consist of just three rings?
Well, it depends on how many electrons you have to place. Okay. So if I have 147 electrons, then I'm going to have a whole lot of rings going out. Your process is going to be exactly the same, but it's going to be just a lot. I'll never make you draw that out or anything like that, but that's the idea. Okay. To kind of show you, well, let's do another example, and then I'll do that. Okay, so normally what I'll do is I'll keep it inside the first 20 for drawing Bohr models, so you don't have to draw a whole bunch of electrons and so forth. Let's go ahead and draw out the Bohr model for boron, B. Okay. So the Bohr model for the element B. So the way you're going to go about this is the very first thing you do is you have to figure out how many electrons you have. So, electrons. How many electrons is boron going to have? Any ideas? Have faith in yourself. 6? 5-ish? 5?
Oh, we have 5, there's no charge.
5. Okay, there is no charge on the boron. Since there's no charge on the boron, your number of electrons is going to be equal to your number of protons, which is your atomic number, which all in all equals 5. Which equals 5. So if we have 5 electrons, on your paper, see if you can draw out what the Bohr model would look like for boron.
I'm sorry, I just have a question.
Of course.
So 5 is the number that's on the left, correct? No.
So you have 5 electrons that you have to place. Okay. So how many electrons are going to fit in the first orbit?
2.
2. Okay. So our first orbit, we're going to put 2 electrons there. Okay. Which leaves how many? 3. So let's make another orbit. How many electrons can that orbit hold? 8. Well, I only have 3 left, so I put 3 in. So this would be the atomic model for boron then. Does everyone agree with that? Okay, let's try one more. Let's do, I don't know, magnesium, Mg. Okay. Draw what the Bohr model would look like for Mg. Make sure everyone's getting started on the right track. Mg is going to have 12 electrons in it. Okay, everyone got their ideas? Okay, so here we go then. Draw our nucleus. The first orbit is going to hold 2. The second orbit can hold up to 8. So 1, 2, 3, 4, 5, 6, 7, 8. And that is 2 plus 8 is 10. So I have 2 more to go. So there we are. So that would be the Bohr model for magnesium. Questions about that? Now, as you can tell, as I've said numerous times, I'm lazy and I don't want to draw out all the E's. So let me show you a shorthand that you can do once you get used to it a little bit. So for magnesium, what you can also do to draw this out is we draw the nucleus, and then we do 2, 8, and 2, something like that. So that way it means 2 electrons in this first orbit, 8 in that, and then 2 in that. It's just a little easier than drawing out all the E's. It's a shorthand approach. Does that make sense? Yeah.
I'm still trying to figure out how you got the 18 for 3.
Okay. So 3 squared is 9. So 3 times 3 is 9. And then times 2 is going to be 18.
Okay, so we don't take each one times the 2 n squared. We take it times the ring that it's in.
Yes. So the ring that it's in squared,
Okay.
and then multiply by 2.
Okay.
So the second ring can always hold only 8. That's its
Mhm.
max capacity.
Yep.
So if you know the max capacity of each one, it's just a process of elimination, right?
It's just a matter of filling them until you run out of electrons.
Right.
Yep. So a lot of students, what they'll do is they actually just memorize 2, 8, 18, 32. But at the same time, I'm perfectly fine with you doing that, but realize it's not just made up numbers. I mean, there is a reason for those numbers there. Even though we don't really go into it, it goes back to this. Now, I've said numerous times that this is really important to understanding chemistry. This was all done from a math approach, okay? Completely done on paper, working out the mathematics and so forth. But to prove to you how important it is to chemistry to some extent, I'm going to show you something about it right away. Looking at the periodic table. The periodic table was done in a completely different country, completely different people, completely different setup, everything about it. We'll talk about the periodic table a lot in chapter 3, actually. But looking at the periodic table, here we go. So here's our periodic table, our friendly periodic table. The first orbit of the Bohr model, how many electrons does it hold? 2, right? Well, going across the first row of the periodic table, we have 1, 2 elements there. And they go back to exactly the same reason why. The second orbit of the periodic table has 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. The third one is 18. Well, you're going to say there's not 18. Well, you haven't learned enough about the periodic table. The 18 that's associated with that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Going across. Okay. And it works out the same. 32. Maybe I can do 32. I'm not going to do above 32. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Going across. So even though the periodic table was derived completely separate of the mathematics in this were not together at all. They show exactly the same thing as we go through it and the reasoning why. So that's true. The orbits as you do it. The other thing about it is this. Boron. Okay, how many rings does it take to draw the Bohr model for boron? Looking up there, there are 2, right? Boron is right here. If you count down, there's 1, 2 rows to get to the boron row. There's 2. Magnesium, how many rings do we have? We have 3 rings. Counting down, 1, 2, 3 to get to it. Okay. Also, along with that, it always allows you to check your number of rings, but also the position. How many electrons are in that outer orbit for boron? 3. Well, if we count over, it's going to be 1, 2, 3 as we count over. Magnesium is going to be 2, 1, 2. So you can always check your Bohr model on the periodic table. Magnesium takes 3 rings, so it's going to be 3 rows down. There are 2 electrons in that outer row, so it's going to be 2 over. So 1, 2, 3 down, 1, 2 over. Okay. Boron is 2 rings, 3 electrons, so 1, 2, 1, 2, 3. If I was to do sulfur, for example, right here, the Bohr model for sulfur is going to have 3 rings, and it's going to be 1, 2, 3, 4, 5, 6 electrons in that outer one. Okay. They match each other perfectly. We'll learn why that is later, but you can always just quickly double check it with the periodic table that way.
So is your cap in your rings going to be 4?
For this class?
Yeah.
Yeah, probably. Yeah, I can't imagine I would do anything past 4. I've never done it before. It's just too much drawing for drawing reasons. If I was really mean, I'd pick like one at the bottom, but that would work out. Actually, as a matter of fact, by the time you get to 4, you covered almost the whole periodic table. Just
So we might even stay within 3 numbers.
Yeah, generally 99% of the time it's going to be number 20 and less. So I guess 19 and 20 maybe is 4, but it doesn't work really well. We'll talk about that later in terms of that. Okay, so one last thing about the Bohr model today, and this has to do with the electrons. The electrons that are in the outer orbit, so these 3 electrons that are in the outer, they have a name associated with them. They're called valence electrons. Valence electrons. And these are why chemistry does what it does. These 90% of chemistry can be explained very easily with valence electrons. And this is actually why we use Bohr model almost all the way through the course, because we just have to understand valence electrons. The 2 on the inside, or any that are on the inside, are called core electrons. So any that are in the outer orbit are called valence, and any on inner orbits are called core electrons. And core electrons we ignore 99% of the time because they're just not interesting. Okay. Do you guys think you have a handle on this? No? Okay. So this is, you guys, we'll end here for today, but this is one of those times in the course where I'm going to beg you guys to practice some of these, drawing these out. Because going forward, we're just going, well, I mean, we'll be doing more practice of it and so forth, but we'll be referring to valence electrons. Like, you need to know how many valence electrons, because that will cause something to happen. If you don't know the number of valence electrons, you can't do that. If you don't know how many electrons an element has, you can't find the valence electrons. You can't find the valence electrons, you don't know why it reacts. So we're getting into the portion now where it builds upon itself. So keep that in mind. And I will be quiet now and then say, enjoy your week. I'll see everyone Thursday.
What about our test?
Oh! I forgot. I totally forgot about it. Okay. Thank you for the reminder. Okay, a couple things about the exams. The multiple choice are worth 1 point each. The fill-ins are worth 2 points each. When the Scantron was scanned, it messed up. So at the bottom of every page, or at the bottom of the Scantrons, there's whiteout over your old score, and then your correct score is over top of it. Don't trust the markings per question. So for example, here in this student's case, if you look at the markings, I don't know if you guys can see it, but almost every one is marked wrong. That's because the Scantron was wrong, not because of the things. So you actually have to go get the key and look at each question. I'm sorry about that, but it's the only thing I could figure out to do. But I did go through and mark them correctly at the end. So the last number should be correct. If you do find a mistake with that, by all means, shout at me and let me know. Yeah.
And the answer keys on what tab in Blackboard?
On Blackboard, old exams, answer keys.
Answer, okay.
Okay. Right off the bat. Also, don't be offended when I pronounce your name wrong. I will. Okay, this one, Kesanet. How do you say that? Kesanet? I just had it. Gary F. Angel B. I'm going to go with Stephen H. David G. And you guys can leave once you have the exams back if you choose. Okay, Evan W. Thank you for saying that. Amber Lee. Catherine D. Troy H.
Crazy.
Phoebe C. Amanda A. Amanda. Right. Joe B. Okay. Here's another one I don't know. G-E-N-E-N.
Wait a second. I probably just wrote my name sloppy. Is it last name Gray?
Yeah.
Yeah, that is me.
G.
Yeah, I probably just
You
like
connected
wrote-
your R.
Oh,
I
I.
never do like my R and I looks
Okay, yeah,
connected.
okay.
That's not a T and I.
Okay, Renisha?
Mine probably like that she.
No, literally, I always put my R
Bryce.
together.
No, you do not.
Christian? Autumn? Jacob? Ariel? Garrett? Ariel?
Wait.
Destiny C. Okay, I'm just reading this thing.
No, you're fine, I can get it.
Amber S. Zachary G.
My R and I be connected. Every time. I can't
Kylie? No?
Yes.
Kylie? Josh S. No? Okay,
Don't beat yourself up either.
Judah?
That's
Okay, I'm running out here, guys. Jacob B. Okay. Dakota. Really? Does that make you Dylan? No? What should be?
What part did you get? Oh, you gave me yours back there. I just want to make sure I understood, so.
Of course.
numbers.
Yeah.
That chart is only to work through it unless you memorize what goes where.
Yes.
Do you find that most people can just basically go, okay, cool, lead, so with lead 82 up here, right?
Yep.
So you have a boat ton of rings at this point, but you just keep working your way out.
Yep. Yeah, and actually with this notation here, it's not hard at all.
I was about to say.
You would just say 2, and you would work your way down until you hit however many extra.
No, but it was
That's
like-
all there is to it.
So
There's
what
a
is
question
the,
that was
okay,
like,
so say
there's
we go
excess
past
water on
4
the river.
rings,
Should
what
we
is,
try it? And it was like,
what is
does
the
this
cap
affect
there?
density?
After
How
32?
does it affect density?
What's the cap at the
It was
next one?
literally, so all we did was just.
Okay,
all we
well, I
did
mean,
was
you
like,
should,
for proton
gosh,
measurements
you've already
and spend
gone
time
from
like
this
trying to separate
32
stuff.
then 50, you could probably get.
Oh, no, you've got 90% of it.
I was gonna say, you're not gonna make
I don't,
rings.
the only ones, like, the 5 would be like RB,
Right?
and then diagonal. So the only ones I wouldn't get are like the 4 on that corner and the 4 on that corner. But I would 3, drawing a bore model, I never asked past 20.
Yeah, but.
And even that, 19 and 20 are kind of long.
That's like the long. Yeah, the
In a
question.
completely unrelated question, did I seem totally did I seem to understand some level?
Well, the major issue here with clock. So 1 gram is equal to 1,000 kilograms, or is 1,000 grams equal to 1 pound? So the kilogram is bigger. The kilogram is bigger.
Oh, it's big, okay.
So it's going to take 1,000 grams for 1 kilogram, which is they're going to flip where you go and so forth.
The middle one kind of.
And this 1,000 centimeters per kilometer, that's
We talk about one thing and then say, right after.
1,000 meters. So I think the process is there. It's just a matter of knowing what numbers to plug in and stuff, which I know that doesn't seem like a good thing at this point, but that's going to be, like, we're not going to be doing metrics and stuff going forward. You will.
Obviously, because it'll be covering multiple chapters, it'll be a more condensed version.
The smaller metric conversion can maybe
I think I ended up getting it with the 4 points. I think I got 74. So, relation to everything is that kind of reliable.
yeah, well, absolutely.
It's not
No, not by any means.
putting copious amounts.
That is, that's a very specific
Now, when it comes to the last quiz, the machine here is obviously have everything in it.
I don't know how
How much would that be?
well, all the quizzes together. So, fifth. But again, it's not, so you think about 25 quizzes,
My mom said, I'm using this on.
the issue is problem. I know. I got my own rules about leaving before Derby.
Oh, I totally get it.